In October of 2019, a machine sitting inside a refrigerated chamber in Santa Barbara, California, accomplished something that should have been impossible. It solved a mathematical problem in 200 seconds. That figure means very little until you hear the second figure. The exact same calculation, if performed on the most powerful classical supercomputer on Earth at that time, a machine called Summit, built by IBM, that occupies a space the size of 2 basketball courts, would have required approximately 10,000 years. Not 10,000 hours, not 10,000 days, 10,000 years. Longer than the entirety of recorded human civilization. Longer than the distance between the invention of agriculture and the moment you are hearing this sentence now. A machine the size of a chandelier, cooled to a temperature colder than the vacuum of outer space, completed in 3 minutes and 20 seconds, what the combined classical computing power of our planet could not complete within the span of human history. And almost nobody outside the world of physics paused to ask the question that should have come next immediately. Where did it do the calculation? That is what this story is really about. Not how the machine works, although we will cover that. Not what it can do, though the implications are staggering. The real question is where, because the answer to that question, if you follow it all the way to its logical conclusion, does not lead you to some new engineering breakthrough. It takes you to the very edge of reality itself. And what it reveals about the nature of the universe you are living in right now is something most people have never been told clearly enough to actually feel the weight of it. Let us begin. The machine was called Sycamore. It was built by Google's Quantum Artificial Intelligence Laboratory, and it contained 53 qubits, the quantum equivalent of the binary bits that power every classical computer you have ever used. A classical bit exists in one of 2 states, 0 or 1. Every computation your phone performs, every photo it stores, every message it sends is encoded as a chain of zeros and ones, processed through logic gates at speeds measured in billions of operations per second. A qubit is different. A qubit can be 0, it can be 1, or it can be both at the same time, in a condition known as superposition, a state in which the qubit holds all possible values simultaneously until the moment it is measured. Once it is measured, that superposition collapses. The qubit becomes a 0 or a 1. But while it is in superposition, while no instrument is observing it, while the universe has not yet forced it to choose, it is both, not metaphorically, not just as a helpful way to think about probabilities, physically, measurably, operationally, both. That property is what gives quantum computers their power. But even the word power is slightly misleading because it sounds like speed. Quantum computers are not just faster versions of classical computers, the way a sports car is a faster version of a sedan. The difference is not one of degree, it is one of kind. A classical computer solving a complex problem works through it step by step, checking one possibility at a time, moving sequentially through a landscape of potential answers until it finds the correct one. A quantum computer does something that has no real classical equivalent. It explores all possible answers simultaneously. Every qubit added to the system doubles the number of states the machine can hold at once. 10 qubits can hold 1024 states simultaneously. 20 qubits can hold over 1 million. 30 qubits over 1 billion. 53 qubits, the number in Google's Sycamore processor, can hold approximately 9 quadrillion states simultaneously. 9 followed by 15 zeros. More simultaneous computational paths than the number of cells in every human body on Earth combined. And that is where the question of where becomes unavoidable, because here is the number that changes everything. If you build a quantum computer with 300 qubits, the number of simultaneous states it can hold is 2 raised to the power of 300. Write that number out, and it has roughly 90 digits. That number is larger than the total number of atoms in the observable universe. Every atom in every star in every galaxy that has ever been detected or mapped or even theorized about. And the 300-qubit machine still has more computational space than all of it combined. You cannot fit that computation inside one universe. There is not enough physical room, not enough particles, not enough space, not enough anything. The computation exceeds the physical resources of the observable cosmos. This is not philosophy. This is arithmetic. If the machine requires more computational states than there are particles in the observable universe to represent them, then the computation is happening somewhere that is not inside the observable universe. And the machine works. It gives correct answers, verified, reproducible, peer-reviewed answers that match the predictions of quantum theory with extraordinary precision. The machine does something that requires resources our universe does not contain, and it does it every single time it runs. The man who predicted this would happen was not surrounded by colleagues and equipment inside a major government lab. He was working alone at night in his house in Oxford, England, where he still lives and still rarely leaves. His name is David Deutsch. In 1985, 34 years before Google's Sycamore demonstrated quantum supremacy, Deutsch published a paper in the Proceedings of the Royal Society of London that almost nobody read at the time. The paper did not propose a faster way to factor numbers. It did not promise to break encryption or simulate molecules. It asked a question that sounded almost philosophical. Is there a physical machine that could in principle simulate any physical process in the universe? Not model it, not approximate it. Simulate it exactly using the actual laws of physics as the operating system. Deutsch's answer was precise and devastating. A classical computer cannot do this. Not because it is too slow, not because we have not built a large enough one, because a classical computer operates inside a single physical reality, and that single physical reality does not contain enough resources. The computation a quantum computer performs exceeds the capacity of our observable universe. So where does the extra computation happen? Deutsch's answer, written plainly in that 1985 paper, was that the calculations happen across multiple versions of reality simultaneously. Not as a metaphor, but as a physical mechanism. The quantum computer, Deutsch argued, is the first device in human history that requires the existence of parallel worlds in order to function. Parallel worlds. The phrase sounds like science fiction. It belongs in a movie, not in a physics journal. But Deutsch was not writing fiction. He was doing physics. Rigorous, peer-reviewed, mathematically formalized physics. And the theoretical structure he described in that paper became the foundation on which every quantum computer ever built has been constructed. He did not merely suggest that parallel worlds might exist. He showed that if quantum mechanics is correct, and 60 years of experimental evidence says that it is, then the only coherent explanation for where quantum computation happens is across multiple instances of reality operating simultaneously and interacting through a process called quantum interference. The wrong computational paths cancel each other out. The correct paths reinforce each other. The answer that appears on your screen is what survives after the physics of multiple realities has been used as a computational resource. The machine does not simply try every answer. It creates conditions in which wrong answers destroy themselves, and correct answers emerge from the interference pattern of parallel computations happening in places you cannot see. That idea, the many worlds interpretation of quantum mechanics, was not originally Deutsch's. It belonged to a man who died without ever knowing that his mathematics would become the foundation of a trillion-dollar technology. His name was Hugh Everett III. He was a graduate student at Princeton University in 1957 when he submitted his doctoral dissertation. The dissertation proposed that when a quantum system is measured and appears to collapse from a superposition of multiple states into a single outcome, the collapse does not actually happen. All outcomes occur. Reality branches. Every possible result takes place in its own version of the universe. The cat is alive in one branch and dead in another. Both branches are equally real. There is no collapse. There is only multiplication. The physicist Niels Bohr, who at the time was the most powerful voice in the field, the architect of the Copenhagen interpretation that dominated quantum mechanics for decades, dismissed Everett's idea. The community followed Bohr. Everett's dissertation was accepted, but his interpretation was treated as a curiosity at best and an embarrassment at worst. He left academic physics almost immediately after receiving his degree. He went to work for the Pentagon, doing mathematical modeling for nuclear weapons targeting strategies. He calculated mortality rates from radioactive fallout. He advised the Eisenhower and Kennedy administrations on hydrogen bomb delivery systems. He drank heavily. He smoked constantly. He barely knew his children. He died of a heart attack in 1982 at the age of 51 on his bed. His son Mark, who would later become the lead singer of a band called Eels, found the body. He has said publicly that he believes it was the first time he had ever touched his father. By Everett's own request, his remains were cremated and his ashes were thrown into the trash. because in the many worlds interpretation, it did not matter what happened to any particular physical configuration. Somewhere in some branch, he is still alive. His daughter Elizabeth took her own life in 1996. A note was found in her purse, saying she was going to join her father in another universe. The many worlds interpretation that Bohr dismissed in 1957 is now, depending on who you ask, the leading theoretical framework for understanding why quantum computers work at all. The computation that cannot fit inside one universe fits because Everett was right. There are other branches, and Deutsch built a machine that uses them. The idea the entire physics establishment rejected for 30 years turned out to be an engineering requirement. The machines require it. They do not work without it. Every quantum computer, in every refrigerated chamber, in every laboratory on Earth, is a physical testament to the mathematics of a man who was effectively buried in the trash by his own request, forgotten by the field he tried to contribute to, and remembered now because the technology proved him right. Before we go deeper, if you are enjoying this journey, do me a small favor and gently like the video and subscribe to Skyline Trek. It may seem like a small thing, but I hold it with real gratitude because every bit of support helps keep this little universe alive. Now think about what this means. We have built a machine that works by reaching into parallel versions of reality and pulling computational resources from places we cannot observe, cannot visit, cannot photograph. The machine does not care whether you believe in parallel universes. It runs, it gives answers, and the answers are correct. IBM disputed Google's claim that the 10,000-year estimate was accurate. They argued that with the right classical algorithm and enough disk storage, their Summit supercomputer could perform the same calculation in 2.5 days. Google acknowledged the revision, but 2.5 days versus 200 seconds is still a factor of more than 1,000, and the problem Sycamore solved was designed specifically to be easy for a quantum machine and hard for a classical one. As quantum hardware improves and the problems become more general, that factor does not shrink, it grows exponentially. Every additional qubit doubles the computational space. Every doubling widens the gap. The curve does not flatten on its own. We are still in the early portion of an exponential trajectory whose endpoint we cannot yet see from where we stand. In December of 2023, IBM unveiled a processor called Condor with 1,121 qubits. In 2019, Google's Sycamore had 53. In just 4 years, the number of qubits in a leading processor grew by a factor of more than 20. That rate of growth exceeded the projections that most quantum computing researchers were making in 2015. The history of exponential technologies is the history of underestimating the back half of the curve. We are good at predicting the next doubling. We are terrible at imagining what the 15th doubling looks like from the third. 15 doublings from 53 qubits is approximately 1.7 million qubits. Most estimates place the threshold for breaking the encryption that protects the modern internet somewhere between 1 million and 4 million physical qubits, depending on error correction requirements. That arithmetic is not a prophecy, it is a rough triangulation. But rough triangulations have a habit of becoming precise once enough data points accumulate. Something is being built that operates at the boundary between our reality and something larger, something that draws its power from a place we cannot access through any other means, something that is growing exponentially and moving toward thresholds the architects of the modern world never anticipated when they designed the systems we now depend on. And the deepest question it raises is not about encryption or computational speed. It is about the nature of the reality you are experiencing right now. Because if the machine works, and it does, and the only coherent explanation for why it works is that it borrows resources from parallel versions of the universe, then those parallel versions are real. Not theoretically real, not usefully real. Real the way the chair you are sitting in is real. Real enough to compute with. Real enough to build a trillion-dollar industry upon. And if they are real, then you are not living in the only version of your life. You are living in one of an inconceivable number of branches, each one as physically genuine as this one. Each one containing a version of you who made different choices at every quantum junction that has occurred since the beginning of time. That is not mysticism. That is the engineering specification of the most powerful machines humanity has ever built. In 1935, a physicist named Erwin Schrödinger sat down to write what he believed would be the final blow against quantum mechanics. He was not trying to support the theory. He was trying to destroy it. The theory had been producing results that matched experiments with extraordinary precision for over a decade. It predicted the behavior of atoms, the spectra of light emitted by heated gases, the stability of molecules, the conductivity of metals. Every test confirmed it. Every measurement agreed with its equations. And yet Schrödinger found one of its central claims philosophically intolerable. The claim was this: a particle does not have a definite state until someone measures it. Before measurement, it exists in a superposition of all possible states at once, not probably in one state or another, not secretly in a state that we simply do not know yet. Genuinely, physically, in all of them simultaneously. The act of measurement does not reveal a pre-existing truth. It creates the outcome. Schrödinger thought this was absurd, and he had a gift for making absurdity visible. So he constructed a thought experiment designed to expose what he saw as a fatal flaw in the theory. He imagined a cat sealed inside a steel box. Inside the box there is a tiny amount of radioactive material. If a single atom of that material decays within 1 hour, a detector triggers a mechanism that shatters a flask of poison, killing the cat. If no atom decays, the cat lives. Quantum mechanics says that the radioactive atom exists in a superposition of both decayed and not decayed until it is observed. Therefore, Schrödinger argued, the cat must be simultaneously alive and dead until someone opens the box. He called this ridiculous. He intended it as a reductio ad absurdum, a logical argument meant to show that a premise leads to a conclusion so outrageous that the premise itself must be false. He was saying to his colleagues, look at what your theory implies, a cat that is both alive and dead at the same time. Surely something has gone wrong here. The physics community absorbed the argument, considered it seriously, and then did the one thing Schrödinger did not expect. They kept the theory. Not because they thought alive and dead cats were sensible, but because every experiment they ran, every measurement they took, every prediction they tested, confirmed that quantum mechanics was correct. The theory worked. It worked with a precision no other theory in the history of physics had ever achieved. And the cat argument, intended as a demolition, became instead the most famous illustration of the very thing it was supposed to destroy. The image of a cat simultaneously alive and dead entered popular culture as a symbol of quantum strangeness. But the physics behind it is not some strange side note. It is the operating principle of every quantum computer ever built. A qubit works exactly like the atom in Schrödinger's box. It is not a zero. It is not a one. It is both simultaneously until the moment you measure it. And while it is in that both state, while the box is sealed, while no instrument has looked inside, it performs calculations across all its possible values at once. That is the source of the computational power we discussed in the first chapter. Not speed, not brute force, the ability to exist in multiple states simultaneously and compute across all of them before collapsing into a single answer when the measurement is made. But here is the question that should follow immediately, and almost nobody asks it out loud. If a qubit is genuinely in both states at the same time, what is it doing between measurements? When no instrument is observing it, when the box is sealed, when the universe itself has not yet demanded a definite answer, what is occurring in the gap between superposition and collapse? Is something real happening there? Or is it just a mathematical convenience, a useful fiction that produces correct answers without corresponding to any actual physical process? The answer physics has arrived at over the last 40 years is unsettling in a way that most popular accounts of quantum mechanics do not properly convey. The answer is that the gap is real. The computation happening between measurements is physically occurring. And the reason it is hidden from us, the reason we do not see cats that are both alive and dead, the reason the world around us appears stable and definite and classical, is not because the superposition is a mathematical trick. It is because of a process called decoherence, and decoherence does not eliminate the other possibilities. It hides them. The physicist who spent his career making this precise was Wojciech Zurek, working at Los Alamos National Laboratory. His work, building on earlier insights by H. Dieter Zeh in the 1970s, provided the clearest and most physically rigorous answer to the question of why the world looks classical when quantum mechanics says it should not. Here is the core of it. A quantum system stays in superposition. stays in that state of multiple simultaneous possibilities, only as long as it remains perfectly isolated from everything around it. The moment it interacts with even a single particle from the outside environment, the superposition begins to dissolve. Not because of any mystical act of consciousness, not because a human mind looked at it, simply because information about the system leaked into the surrounding world. Think about what this means physically. Your coffee cup is a quantum system. It is made of atoms, and atoms obey quantum mechanics. In principle, your coffee cup could exist in a superposition of being on the table, but it is constantly interacting with trillions of particles every second. Air molecules bounce off its surface. Photons from the lights in the room strike it. Thermal vibrations in the table pass through it. Each interaction carries away a tiny piece of quantum information. Each interaction entangles the cup with another particle in the environment, and once that information leaks out, the superposition is destroyed. The coffee cup's quantum state decoheres. It selects a definite position. It becomes classical. For your coffee cup, this process happens in approximately a trillionth of a second. Decoherence is effectively instantaneous at the scales of ordinary objects. That is why you have never seen a coffee cup in two places at once. Not because quantum mechanics does not apply to coffee cups, it does, but decoherence destroys the superposition so quickly that it is as if it never existed. The classical world you experience, the world of definite objects in definite positions with definite properties, is not the fundamental reality. It is what quantum reality looks like after decoherence has done its work. It is the surface. The quantum superposition beneath it is the depth. Now here is where this connects directly to quantum computers and to the question we raised at the beginning. To keep a qubit in superposition long enough to actually compute with it, you have to isolate it from everything. Perfectly. Completely. No stray photon can touch it. No vibration can reach it. No thermal fluctuation can brush against it. The machines that Google and IBM build are cooled to temperatures colder than the vacuum of deep space, to approximately 15 millikelvin, roughly 1/100th of a degree above absolute zero. At that temperature, almost all thermal motion stops. The particles in the machine barely move. The environment is as quiet as physics allows. And in that silence, the qubits hold their superposition long enough to perform calculations that no classical computer can match. The entire engineering challenge of quantum computing can be reduced to a single sentence. Keep the computation hidden from the universe long enough to get an answer. That is it. Every cryogenic system, every electromagnetic shield, every vacuum chamber, every vibration isolation platform, in every quantum computing laboratory on Earth, exists for one purpose: to prevent the environment from looking at the qubits before the calculation is finished. Because the moment the environment looks, the moment a single particle of the surrounding world interacts with the qubit and carries away even one bit of quantum information, the superposition collapses. The computation is ruined. The answer is lost. Think about what that means in the context of Deutsch's argument about parallel worlds. The computation happens while the qubits are in superposition, while they are isolated, while no instrument in our universe is observing them. The answers that emerge when we finally measure the qubits come from a process that occurred entirely behind a wall of isolation, in a space where the rules of classical reality do not apply, where the qubits existed in all their possible states simultaneously and computed across all of them. When we measure the result, we get one answer, but the process that produced that answer involved a number of simultaneous computational paths that exceeds the number of atoms in the observable universe. If you take the Copenhagen interpretation, the traditional view of quantum mechanics, those other computational paths simply vanish when the measurement is made. They were just probabilities, and the act of measurement selected one outcome and discarded the rest. But that interpretation has a problem. It does not explain where the computational work happened. It does not account for the resources. If the machine explored more paths than there are atoms in the universe, and the answer it returned is demonstrably correct, then something did the exploring. Something performed the work. And if our universe does not have enough room to contain that work, then either the work happens somewhere else or the machine should not function. The machine functions. If you take the many worlds interpretation, Everett's view, the other computational paths do not vanish. They continue to exist in other branches of reality. The measurement does not collapse the superposition. It entangles the observer with one particular branch. In all the other branches, other versions of the measurement are being made, producing other answers in other versions of the laboratory, observed by other versions of the researchers. Decoherence is the process by which these branches become invisible to each other. The wall goes up, the branches separate. Each observer sees a single definite classical result, but the other branches are still there, still real, still carrying the computational work that produced the answer. This is the choice quantum computing forces upon us. Either the machine works by magic, performing calculations with resources that do not exist, or the machine works by physics, using resources that exist in places we cannot directly observe, but whose reality is confirmed every time the machine returns a correct answer. There is no comfortable middle ground. There is no interpretation that makes the computational work disappear without also making the machine stop working. The machine works. The resources exceed our universe. The question of where remains open only if you are willing to leave it open. If you follow the physics to its conclusion, the answer is the same answer Deutsch gave in 1985 and Everett proposed in 1957. The computation happens across branches of reality we cannot see, because decoherence has built a wall between us and them. A wall not made of matter or energy, a wall made of leaked information, a wall that quantum engineers spend billions of dollars maintaining every year, because the moment the wall comes down, the computation ends and the quantum advantage disappears. We are building machines whose most powerful operations occur behind a wall that separates our branch of reality from the branches that do the work. We deliberately hide our most consequential calculations from the observable universe. And the thing that makes the wall necessary, decoherence, the process by which quantum information leaks into the environment and superpositions collapse, is the exact same process that makes the world look classical, solid, and definite to you right now. The reason you see one world instead of many is the same reason a quantum computer needs to be colder than outer space. Decoherence, the wall between worlds. Schrödinger wanted to show that quantum mechanics was broken. What he showed instead was that the world is not what it appears to be. The cat is not a paradox. The cat is a description of what reality does when nobody is looking. And the machines we have built prove that what reality does when nobody is looking is far more vast, far more structured, and far more real than anyone in 1935 could have imagined. The question is no longer whether the other branches exist. The question is, what else is happening in them that we have not yet learned to detect? Before any of this was built, before refrigerated chambers and superconducting circuits, before Google and IBM and the trillion-dollar industry that now surrounds quantum computing, someone had to explain how. Not where the computation happens. We have covered that. Not why it is powerful. We have covered that too. But how? What is the actual physical mechanism by which a quantum computer takes a problem with more possible answers than there are atoms in the observable universe, and returns one correct result? The counting argument tells you that the resources exist somewhere beyond what our universe can contain. The many worlds interpretation tells you those resources live in parallel branches of reality. But neither of those tells you how the machine uses them. How does it reach into those branches and come back with an answer? How does it sort through an incomprehensible number of possibilities and find the one that is correct? The answer to that question came from Richard Feynman, and in my view it is the most beautiful and the most disturbing idea in the entire story. In 1982, Feynman gave a talk at the MIT Physics of Computation conference that would later be published in the International Journal of Theoretical Physics. The talk was titled, Simulating Physics with Computers. Feynman was not a computer scientist. He was a physicist, widely regarded as one of the most brilliant and unconventional thinkers of the 20th century. He had worked on the Manhattan Project as a young man. He had revolutionized quantum electrodynamics, the theory describing how light and matter interact, work for which he received the Nobel Prize in Physics in 1965. He had a reputation for cutting through complexity with an almost physical intuition for how nature actually works beneath the mathematics. And in that 1982 talk, he made an observation that sounds simple but contains an entire revolution. Feynman pointed out that classical computers cannot efficiently simulate quantum systems, not because they are too slow, but because the problem grows exponentially with the number of particles. Simulate one electron and you need to track two possible states. Simulate 2 electrons, and you need 4. 10 electrons, 1024. 20 electrons, over a million. 30 electrons, over a billion. 100 electrons. And the number of states you need to track exceeds the number of atoms in the observable universe. Classical computers cannot handle this. Not because of engineering limits, but because the structure of classical computation does not match the structure of quantum reality. You cannot simulate a quantum world with a classical machine any more efficiently than you can describe a symphony by reading its sheet music one note at a time. The information is there, but the form is wrong. Feynman's proposal was elegant and radical. If you want to simulate quantum physics, build a machine that runs on quantum physics. Let the computer itself be made of quantum mechanical elements that obey quantum mechanical laws. Let the machine be the thing it is studying. And embedded in that proposal was an insight about mechanism that turned out to be the key to everything that followed. The mechanism is called interference. Think about 2 waves on the surface of water moving toward each other. Where the peak of one wave meets the peak of another, they combine and produce a higher peak. Where a trough meets a trough, the result is a deeper trough. Where a peak meets a trough, they cancel each other out. The water goes flat. The waves do not disappear. They do not stop existing. They destroy each other through the precise alignment of their opposite phases. This is interference. It happens with water waves. It happens with sound waves. It happens with light. And it happens with quantum probability. A quantum computer is engineered so that all the computational paths leading to wrong answers cancel each other out, like a peak meeting a trough on the surface of water. And all the paths leading to the correct answer reinforce each other, like 2 peaks combining into a larger peak. The machine does not try every possible answer and then check which one is right. It does not search through a list. It does not guess. It is structured at the level of its physical design so that wrong answers destroy themselves through interference before the calculation is complete. What arrives at the end, the single answer the machine produces when you measure the qubits, is not a lucky guess. It is what survives. It is the final thing standing after everything incorrect has been systematically eliminated by the physics of the computation itself. Pause on that for a moment. The machine does not select the right answer. It creates conditions in which wrong answers cannot survive. The wrong answers annihilate each other. They cancel. They subtract themselves from reality through the quantum mechanical process of destructive interference. And the right answer emerges, not because anyone chose it, but because it is the only path through the computation that survives its own physics. This is not a metaphor. This is the literal operating principle of every quantum algorithm ever designed. Feynman saw this possibility in 1982. 3 years later, Deutsch formalized it, and in the decades that followed, a series of algorithms were developed that exploited interference in increasingly powerful ways. The most famous of these was published in 1994 by a mathematician named Peter Shor. Shor wrote an algorithm, a set of instructions that a quantum computer could follow to break apart any large number into the prime numbers that multiply together to produce it. On the surface, this sounds like an abstract mathematical exercise with no connection to daily life. The connection becomes visible the moment you understand how the modern world protects its secrets. Almost all of the encryption that secures the internet, the mathematical layer that keeps your bank account separate from everyone else's, that protects private communications, that guards the infrastructure of governments and militaries and hospitals and power grids, is built on a single assumption. The assumption is that multiplying 2 large prime numbers together is easy. But working backward from the result to find those original primes is practically impossible. A classical computer attempting to factor a number with several hundred digits would need longer than the age of the universe to find the primes. The entire architecture of digital security rests on this computational asymmetry. Easy in one direction, effectively impossible in reverse. Shor's algorithm removes that asymmetry. A sufficiently powerful quantum computer running Shor's algorithm could factor those large numbers not in thousands or millions of years. The encryption that protects modern civilization, built over 50 years on the assumption that prime factorization is computationally infeasible, becomes transparent, breakable, open. The lock that guards every digital secret in the world has a key, and Shor showed exactly what that key looks like. The key does not yet exist in physical form, because no quantum computer today has enough qubits to run Shor's algorithm at the scale required to break real-world encryption. But the blueprint exists. The mathematics is published, and the machines are growing. 2 years after Shor, in 1996, a researcher named Love Grover published a second algorithm that addressed something broader than factoring numbers. Grover's algorithm addresses search. Imagine an unsorted list containing 1 billion items, and you are looking for one specific entry. A classical computer has to check the items one by one. On average, it finds the target after checking half the list. 500 million checks. Grover's algorithm finds the item in roughly the square root of 1 billion checks, about 31,600. Not because it moves faster through the list, but because it uses quantum interference, the same mechanism Feynman described, to amplify the probability of the correct answer and suppress the probability of every wrong answer simultaneously. Every wrong item in the list cancels itself out. The right item reinforces itself. The machine does not search. It creates conditions in which everything that is not the answer becomes invisible. The asymmetry Grover creates is not as dramatic as Shor's. It provides a quadratic speedup, squaring the efficiency, rather than reducing exponential time to manageable time. But it applies universally. Any search problem, any database, any collection of data with hidden structure waiting to be found, Grover's algorithm accelerates the discovery of that structure in a way that is not about better engineering. It is about fundamental physics. The universe allows quantum search to be faster than classical search, because the universe itself runs on quantum rules. The machine is not outsmarting reality. It is aligning itself with reality's operating system and using interference, the same process that makes waves cancel on water, to eliminate the noise and reveal the signal. Now step back and look at the full picture that has assembled itself across these chapters. We have a machine that uses resources from beyond the observable universe. It draws its power from parallel branches of reality that decoherence hides from our everyday perception. It operates by creating conditions where wrong answers destroy themselves through quantum interference, leaving only the correct result. It can, in principle, break the encryption that protects the entire modern world, and it can search through any collection of data faster than any classical system that has ever existed or could ever exist. This is not a future technology. The algorithms exist. The machines exist. They are growing. And the question that follows from all of this is not a question about physics or mathematics or engineering. It is a question about information itself, about what information is, about whether information is something we extract from reality, the way you might harvest wheat from a field, or whether information is reality, whether the physical world you experience is made of matter and energy, or whether matter and energy are themselves made of something deeper, something that the quantum computer touches every time it runs, something that a physicist named John Wheeler spent 60 years trying to name. He called it the most fundamental substance in the universe. He called it the thing from which all physical things emerge, and he gave it a name that sounds like a riddle but was meant as a precise physical statement. He called it from bit. John Archibald Wheeler spent 60 years working at the center of theoretical physics. He coined the term black hole. He worked with Niels Bohr to explain nuclear fission. He supervised the doctoral dissertations of Richard Feynman and Hugh Everett, two of the most important minds in the history of quantum theory. He contributed to the Manhattan Project. He shaped the development of general relativity for an entire generation. By the time he reached the final decades of his career, he had spent more time thinking seriously about the foundations of physical reality than almost anyone who has ever lived. And the conclusion he arrived at was not a formula. It was not an equation. It was a statement so compressed it fits into 3 words. It from bit. Every it, Wheeler wrote, every particle, every field of force, even the space-time continuum itself derives its function, its meaning, its very existence entirely, even if in some contexts indirectly, from the apparatus elicited answers to yes or no questions, binary choices, bits. All things physical are information theoretic in origin, and this is a participatory universe. Read that again slowly. Wheeler is not saying that information is useful for describing the universe. He is not saying that physics can be expressed in terms of information. He is saying the universe is made of information. That matter, energy, space-time, the physical world in its entirety, emerges from something more fundamental. And that fundamental thing is not a particle. It is not a wave. It is not a string or a field or a brain. It is an answer, a yes or a no, a bit. This is a genuinely strange idea to sit with, because it reverses the intuition most of us carry around without ever examining it. We tend to think of reality as the solid ground, and information as something we extract from it. We think of atoms as primary, and descriptions of atoms as secondary. The rock comes first. The measurement of the rock comes later. Wheeler is saying the measurement comes first. The rock comes later. The information is primary. The physical world is what happens when enough bits accumulate in the right configuration. There is nothing underneath the information. No deeper layer. No hidden substrate. The answers are the substance of reality. Now bring that idea into contact with everything we have been building toward. If the universe is made of information, then a device that manipulates information at the most fundamental physical level is not modeling reality. It is not simulating reality. It is operating on the actual substrate from which reality is constructed. Every calculation a quantum computer performs is an intervention in the informational fabric of the universe itself. That is not a poetic description. If Wheeler is right, it is a literal one. The quantum computer is not a tool that works within reality. It is a tool that works on reality. At the level where reality is being assembled from yes or no answers, the quantum computer is adding its own answers to the conversation. Wheeler was not a fringe figure making provocative claims for attention. He was one of the most respected and credentialed physicists of the 20th century, the doctoral supervisor of Feynman, the collaborator of Bohr and Einstein, the man who named the black hole. He spent 6 decades working his way to this conclusion, and when he arrived, he stated it plainly. The universe is information processing itself into existence, and we are participants in that process, not observers standing outside it. There is a piece of experimental evidence that supports this picture so directly that it deserves its own examination. In 1961, a physicist named Rolf Landauer at IBM Research published a paper arguing that information is not abstract, it is physical, and he had a specific measurable way to demonstrate this. When you erase a single bit of information, when you take a system that holds a 1 or a 0 and reset it to a known state, you release heat. Not metaphorically, literally. A tiny but measurable and theoretically unavoidable amount of thermal energy is discharged into the surrounding environment. This became known as Landauer's principle. The act of erasing information is physically irreversible, and irreversibility has a thermodynamic cost that cannot be designed away or eliminated by better engineering. Information erasure produces heat the way friction produces heat. It is a law. For decades, Landauer's principle remained a theoretical prediction without direct experimental confirmation. The amount of heat released by erasing a single bit is extraordinarily small, on the order of 3 × 10⁻21 joules at room temperature. Measuring this requires instruments of almost inconceivable precision. Then, in 2012, a team led by physicist Eric Lutz built an experiment delicate enough to do it. They trapped a single microscopic particle in a well created by focused laser beams, manipulated it to erase 1 bit of information, and measured the heat released. The result matched Landauer's formula. Information has weight. Information has temperature. Information has a physical cost embedded in the laws of thermodynamics. Deleting a fact about the universe releases energy into the universe. The information is not just a description of the physical world, it is part of the physical world. Wheeler's intuition, stated in 1990, was confirmed in a laboratory in 2012. Now connect this to quantum computers. A quantum computer operating in superposition is, in a certain sense, not yet committing to answers. It is holding multiple possibilities open simultaneously before collapsing into a result. Some researchers have suggested that this might allow quantum computations to approach a kind of reversibility that classical computation cannot achieve, potentially sidestepping some of Landauer's heat cost. If that is true, then quantum computation is not just faster than classical computation. It is operating closer to the theoretical minimum energy cost that physics allows. It is computing in a way more aligned with how the universe itself processes information than anything we have built before. The machine is not brute forcing its way to an answer. It is whispering to reality in reality's own language, and reality is answering back. But there is another thread that connects Wheeler's information universe to quantum computing, and it is one most people have never heard discussed outside advanced theoretical physics seminars. It is called the holographic principle, and it suggests that the relationship between information and the physical world is even stranger than Wheeler imagined. In the 1990s, two physicists, Gerard Hooft and Leonard Susskind, working independently, arrived at a conclusion that sounds on first encounter like it cannot possibly be meant literally. It is meant literally. The holographic principle states that the maximum amount of information that can be contained inside any region of space is not determined by the volume of that region. It is determined by the area of its surface, not the inside, the boundary. You would expect that doubling the volume of a box would double the information it can hold. More space, more room for particles, more information. The holographic principle says no. The information capacity scales with surface area, not volume. All the information describing everything that happens inside a given region of space is fully encoded on the two-dimensional surface surrounding it. The interior is not the primary thing. The boundary is. This was not derived from philosophy. It was not a thought experiment. It was calculated from the physics of black holes. When matter falls into a black hole, the information it carries does not disappear into the interior. It is encoded on the event horizon, the two-dimensional surface marking the boundary of the black hole. The amount of information a black hole can contain is proportional to the area of its event horizon, not the volume enclosed within it. Hooft and Susskind generalized this result and proposed that the same principle applies to any region of space, not just black holes. The three-dimensional world inside any volume is fully described by information encoded on its two-dimensional boundary. Space, as we experience it, may be a kind of projection, not an illusion, but something more like a derived object, something emerging from a more fundamental layer of information encoded elsewhere. Which means that when a quantum computer manipulates information at the most fundamental physical level, it may be operating at a layer of reality that is more basic than space itself, not inside space, but underneath it. The computation is not happening in a location. It is happening at the level from which locations emerge. That sentence is worth hearing again, and the question that follows from it is one I do not think we have adequately confronted as a civilization. If the universe is information, if that information is encoded holographically on boundaries rather than distributed through volumes, if quantum computers The public conversation about quantum computing tends to treat it as a future concern, something to think about eventually. The NIST competition is institutional proof that some very serious people do not share that timeline. And here is the layer underneath that, which is harder to set aside. The competition was launched in 2016. The standards were published in 2024. The systems that need to be updated to use those standards, the actual infrastructure of the internet, banking, government communications, military networks, hospital databases, power grids, will take years more to retrofit, which means there is a window, a gap between when quantum machines become capable enough to break current encryption and when the new encryption is actually installed everywhere. How long is that window? Who knows exactly how wide it is, and who right now is paying very close attention to its edges? The term cryptographers use for this gap is harvest now, decrypt later. The concept is simple. You do not need a quantum computer today to steal tomorrow's secrets. You collect the encrypted data now. You store it. You wait. The data sits on servers, on hard drives, in archives, on tapes. It is encrypted. It is unreadable. It is safe by today's standards. And then at some point in the future, when a quantum computer powerful enough to run Shor's algorithm at scale becomes available, you run the stored data through it. The encryption opens. The data becomes readable. Every email, every transaction, every classified communication, every medical record, every state secret, everything that was encrypted with the algorithms Shor proved breakable in 1994 becomes transparent. Not in the future. Now, because the data was already collected, the lock will open. The only question is when. Who is collecting? That question is less comfortable than the technical ones. Nation-states with advanced intelligence capabilities have the resources and the motivation to harvest encrypted communications at scale. The infrastructure exists. The legal frameworks for bulk data collection have been debated, litigated, and in many cases authorized in different jurisdictions. Storage is cheap. Patience is not in question. If your government's encrypted communications with its allies are being intercepted and stored by a strategic competitor, and that competitor is investing billions of dollars in quantum computing research, the timeline for decryption is not abstract. It is budgetary. It is a line item in a national security plan. But the cryptographic threat, as alarming as it is only the most concrete expression of something deeper. The real story of quantum computing's impact is not about what it can break. It is about what it can see. Grover's algorithm, the quantum search algorithm we discussed in the previous chapter, does not just apply to databases and password cracking. It applies to pattern recognition, to finding hidden structure in data, to identifying correlations that no classical system could detect because the classical search space is too large and the patterns too subtle. A quantum computer running Grover's algorithm across a sufficiently large dataset does not just find what you are looking for faster, it finds things you did not know were there. Consider what that means for fields beyond cryptography. Drug discovery. The interaction between a candidate molecule and a protein receptor involves quantum mechanical effects that classical computers cannot fully simulate. The number of possible molecular configurations for a single drug candidate interacting with a single receptor site exceeds the computational capacity of every classical supercomputer on Earth combined. Quantum computers, built on the same physics that governs molecular interactions, can simulate these systems natively, not by approximation, but by running the same quantum rules that the molecules themselves obey. Richard Feynman's original insight from 1982 was precisely this. If you want to simulate quantum physics, build a machine that runs on quantum physics. The pharmaceutical industry has recognized this. Every major drug company has a quantum computing research program. The potential to reduce drug development timelines from decades to years, to identify therapeutic compounds that classical screening would never find, to simulate biological processes at the molecular level with full quantum fidelity, represents a transformation as fundamental as the invention of the microscope. Material science. The properties of a material, its conductivity, its strength, its superconducting temperature, its capacity to store energy, are determined by the quantum mechanical behavior of its electrons. Designing a new material with specific desired properties currently requires years of experimental trial and error, because the quantum simulation of electron behavior in a crystal lattice computationally intractable for classical machines. A quantum computer could simulate these systems directly, predicting the properties of materials that have never been synthesized, identifying superconductors that operate at room temperature, designing batteries with energy densities that transform the economics of renewable power. The engineering implications are not incremental, they are civilizational. Climate modeling. The behavior of atmospheric systems involves interactions between trillions of molecules at the quantum level. Current climate models are forced to use approximations and averages because the full quantum simulation of atmospheric chemistry is beyond classical reach. Quantum computers could model these interactions with a fidelity that reveals dynamics invisible to current simulations, potentially identifying tipping points, feedback loops, and mitigation strategies that today's models cannot resolve. And then there are the applications nobody has thought of yet. This is the part that deserves the most attention and receives the least. Every truly transformative technology in history has produced consequences its creators did not anticipate. The inventors of the printing press did not foresee the Protestant Reformation. The designers of the Internet did not predict social media. The engineers who built the first transistor did not imagine a device in every pocket containing more computing power than the Apollo program. The fundamental physics is understood. The engineering is progressing. The early applications are being explored. But the applications that will define the technology, the ones that will reshape economies and institutions, and the daily experience of being alive, have not been conceived yet. They will emerge from the intersection of quantum capability with problems we do not currently think of as solvable. The machines are growing. In 2019, 53 qubits. In 2023, 1,121. In 2024, Microsoft announced the first topological qubit, a qubit protected from errors not by shielding, but by the geometry of space itself. A qubit that is stable, not because it is hidden, but because the information it carries has no single location. It exists in the relationship between particles that can be physically separated. An error would have to corrupt both locations simultaneously to destroy the information. Ordinary environmental noise cannot do this. The qubit becomes stable because it is nowhere in particular. This is no longer just an engineering challenge. This is a new kind of object, a thing whose defining property is distributed across space in a way with no classical analog. The growth is not linear. It is not even cleanly exponential. It is something more complex, driven by simultaneous advances in hardware, error correction, algorithm design, and the sheer volume of investment pouring into the field from governments and corporations that understand what is at stake. China has launched a quantum satellite. Europe has funded a €1 billion quantum flagship program. The United States has passed the National Quantum Initiative Act. Every major technology company on Earth has a quantum computing division. The race is not coming. The race is here. And the finish line is not a faster computer. The finish line is the ability to manipulate information at the level where reality is assembled. We return to the question that has been building since the first chapter. What are the consequences of building a machine that operates at the boundary between our reality and the informational substrate from which reality emerges? The encryption question has an answer. The answer is NIST's new standards and the decade-long transition to quantum-resistant cryptography. The drug discovery question has a timeline, 5 to 15 years before quantum simulations meaningfully accelerate pharmaceutical research. The material science question has a roadmap. Quantum advantage for certain materials problems may arrive within the next decade, but there is a consequence that has no answer, and no timeline, and no roadmap. And it is the consequence that connects everything in this story to the question of what kind of universe you are living in. If the machine reaches into parallel branches of reality to perform its computations, if it uses the structure of the multiverse as a computational resource, if it operates at a level of reality more fundamental than space itself, then every increase in the machine's power is an increase in the depth of our interaction with the substrate of existence. Every additional qubit widens the channel between our branch and the others. Every computation draws on resources that exist in places we cannot observe, but that are real enough to return correct answers. We are building a wider and wider doorway into the architecture of reality, and we have never stopped to ask what else might come through. David Deutsch does not fly on airplanes. He rarely leaves Oxford. He works at night. He has described himself as someone who finds it easier to think about abstract structures of reality than to navigate the practical demands of ordinary social life. He is also, by most accounts of people who work in quantum computing, one of the 2 or 3 people most responsible for the fact that the field exists at all. His 1985 paper laid the theoretical architecture. His later decades of work have continued pushing at the same question from different angles. And throughout all of it, he has maintained a position that many physicists privately agree with but few are willing to state as plainly as he does. He genuinely believes the many worlds interpretation is correct, not as a working assumption, not as a useful framework, as a description of actual reality. He believes that when a quantum computer runs, the computation happens across a vast number of parallel versions of the universe simultaneously, that those parallel instances are as real as this one, and that the machine is genuinely reaching into that parallel structure and extracting answers. He believes this the way most people believe the chair they are sitting on is real. And the machine he helped design works. It gives correct answers. It outperforms classical computers on problems that can be independently verified. If the machine works, and the only coherent explanation for why it works requires parallel universes, then the question is not whether parallel universes exist. The question is what it means that we built a device that uses them, and what it means that we did this without most of the world understanding what we actually built. Here is what we have established across the course of this story. In 1982, Feynman proposed that quantum systems cannot be efficiently simulated by classical computers, and that the solution is to build machines that operate by quantum rules. In 1985, Deutsch formalized the concept of a universal quantum computer and argued that its operation requires the existence of parallel realities. In 1994, Shaw demonstrated that a quantum computer could break the encryption protecting the modern world. In 1996, Grover demonstrated that quantum search could find hidden structure in data faster than any classical method. In 2019, Google's Sycamore processor performed a computation in 200 seconds that the best classical estimate suggested would take thousands of years. In 2024, NIST published post-quantum cryptography standards after an 8-year international competition to prepare for the threat. And throughout all of this, the physics has pointed consistently in one direction. The universe is not what it appears to be. It is larger, stranger, and more deeply structured than the classical picture we grew up with ever suggested. The question I keep coming back to is this: what does it mean to live inside a reality that a machine can reach beyond? What does it mean that the chair you are sitting on, the room you are in, the body you inhabit, exist in one branch of a structure so vast that its computational capacity exceeds the number of atoms in the observable universe? What does it mean that there are versions of you right now in other branches who made different choices at every quantum junction since the moment of your conception? Not metaphorically, not as a thought experiment, as the engineering specification of a working machine. The many worlds interpretation does not say that parallel universes are possible. It says they are necessary. The machine requires them. Without them, the computation has no place to happen. Without them, the answers have no origin. The mathematics is not ambiguous. The experiments are not equivocal. The machine runs. The answers are correct, and the resources exceed our universe. And the only coherent framework that accounts for all of this simultaneously is the one Everett proposed in 1957. The one Bohr dismissed. The one Deutsch built a machine to exploit. Reality branches. Every quantum event produces all possible outcomes. The outcomes do not cancel. They coexist. And we are one branch among an inconceivable number. Everett died on his couch in 1982. He was 51. His ashes were thrown in the trash at his own request, because he believed that in the many worlds interpretation, no particular physical configuration matters. Somewhere in another branch, he is still alive. Somewhere in another branch, he stayed in physics. Somewhere in another branch, Bo listened. Somewhere the many worlds interpretation was accepted in 1957 instead of dismissed, and the quantum computing revolution began 40 years earlier than it did in our branch. We cannot reach those branches. We cannot communicate with them. But according to the physics that powers every quantum computer on Earth, they are there. They are real. And the machine we built touches them every time it runs. His daughter Elizabeth took her own life in 1996. She left a note saying she was going to join her father in another universe. His son Mark became the lead singer of a band called Eels, and has spent his career processing the experience of growing up with a father who was physically present but emotionally absent. A man who understood the structure of reality better than almost anyone alive, but could not navigate the structure of a family. The many worlds interpretation says Elizabeth is alive in another branch. It says every version of her life that was physically possible exists somewhere in the branching structure of the multiverse. Whether that is comforting or terrifying depends on how much weight you give the word real when it is applied to a place you can never visit. There is a physicist at MIT named Seth Lloyd who in 2006 calculated something that puts a number on everything we have been discussing. He calculated the computational capacity of the observable universe. The answer is approximately 10 to the 120 operations performed over the entire 13.8 billion year history of the cosmos. Every electron, every photon, every quark performing its quantum interactions is, in Lloyd's framework, executing a computational operation. The universe is not like a computer. It is one. It has been running since the Big Bang, using every physical interaction as a step in a calculation whose output is the reality you are experiencing right now. Now place our quantum computers inside that picture. We are building devices that operate on the same physical principles as the universe's own computation. They use the same quantum mechanical rules, the same superposition, the same entanglement, the same interference. They are not modeling the universe from outside. They are participating in it, adding their operations to the total, becoming in a small but physically real sense part of the universe's ongoing calculation, which raises a question that deserves more attention than it receives. If the universe is computing something, and we add our own quantum computation to that process, do we change the output? Is the trajectory of the universe's calculation altered by what we compute inside it? And if so, in what direction are we pushing it? We started this story with a number, 200 seconds against 10,000 years, a gap so large it seemed like a measurement error rather than a physical fact. But it was not an error, it was a data point, and every data point we have examined since has pointed in the same direction. The machine works because it reaches beyond our universe. The information it manipulates may be the primary substance of reality. The encryption that protects the modern world has been living on borrowed time since 1994. The institutions that should be preparing are only now beginning to move. And the deepest implication of all, the one beneath every technical detail and every policy discussion, is that we have built a tool that interacts with the fabric of existence at a level more fundamental than space and time. We did not build this tool because we fully understood what we were building. We built it because the physics worked, because the equations predicted it, because the experiments confirmed it, because the engineers solved one problem at a time without necessarily confronting the full scope of what they were constructing. And now the tool exists. It is growing, it is doubling, it is approaching thresholds that will reshape cryptography, medicine, material science, artificial intelligence, and the global balance of power. But the question that should keep you thinking long after this story ends is not about any of those applications. It is simpler and more fundamental than all of them combined. We built a machine that works by reaching into parallel versions of reality. We confirmed that it works. We verified the answers. We published the papers. We built the industry. And we never asked the most basic question of all. If we can reach them, can they reach us? If the computation draws on resources from other branches, does the interaction go both ways? Is the doorway we opened a one-way glass, or is it a window? The physics does not answer that question. Not yet. The mathematics of quantum interference describes how information from parallel branches combines to produce a result in our branch. It does not describe what happens in the other branches after the computation is complete. It does not tell us whether the act of quantum computation, of reaching into the multiverse and extracting an answer, has consequences that propagate back through the branches we drew from. It does not tell us whether the branches notice. Deutsch has worked on this problem for 40 years. He has not solved it. No one has. The question remains open at the deepest level of theoretical physics, and it will remain open as the machines grow larger, as the qubits multiply, as the computations become more complex, as the channel between our branch and the others widens with every advance in quantum hardware. We are reaching into the structure of reality and pulling out answers. The answers are correct. The machine works. And somewhere in the space between the question and the answer, in the gap where the computation happens, and the interference eliminates the wrong paths and the right path survives, something is occurring that we have not yet learned to describe. Something that involves every version of the machine in every branch of reality, coordinating their operations through the physics of interference to produce a single result that arrives on a screen in a laboratory in our world. The machine is running right now, in refrigerated chambers colder than outer space, in laboratories funded by governments and corporations, in research programs both classified and unclassified. It is pulling answers from places we cannot see. It is using the architecture of reality as a computational resource, and it is growing. Everett believed that every branch of reality is equally real. Deutsch believes it too. The machine they made possible does not care what you believe. It runs. It returns correct answers. And the place where those answers come from is not inside this universe. What do we do with that? What does a civilization do when it discovers that the most powerful tool it has ever built works by reaching beyond the boundary of everything it can observe? What does it mean to be a species that can touch the multiverse but cannot see it, that can use it but cannot visit it, that can extract from it but cannot know what it takes in return? The machine is running, the door is open, and the only honest thing to say is that we do not know what is on the other side. We only know that the answers keep coming back, and that so far they have been correct. So far.